My name is Katie Templeton. I am doing my master's degree in environmental science, and I did my project on nuclear energy waste and containment. So, starting off with just some basic nuclear energy history. Nuclear energy and fission was first discovered by Otto Hahn in 1938, and that is a lovely picture of him. And then just 4 years later, in 1942, the first self-sustaining reactor was built on the University of Chicago's campus by Enrico Fermi and Leo Szilard, and a picture of that is right below the picture of Otto Hahn. And then only 3 years later, in 1945, the first atomic bomb was dropped on Hiroshima by the United States. It was nicknamed Little Boy, and you can see a replica of the bomb in that picture beside Otto Hahn. Little Boy was developed by the Manhattan Project and built in Oak Ridge, Tennessee. And then 6 years after that, there was a significant shift in nuclear research, and that's when nuclear energy was really born. And that is when a reactor powered light bulbs for the first time. And that is the picture below the bomb. And that happened in 1951. So I mentioned fission, but what is fission? So fission is neurons being fired at an element's nucleus. This neuron forces the nucleus to break apart, producing radioactive isotopes and other elements, as well as energy. Like I said, the products are radioactive and are highly unstable. So what is nuclear waste? The easy answer is it is the product of nuclear fission. But when we think of nuclear waste, we think about the picture that you see there with the barrels of hazardous material that are bright yellow and painted black. However, that's not exactly what it looks like these days. There are two types of nuclear waste, low level and high level. And the levels refer to how radioactive the waste material actually is. So low-level waste are things that have become contaminated due to exposure, like gloves, masks, suits, anything that's not the nuclear material itself. High-level waste are the products of the fission reaction that control rods, and other materials used in the reactors. And the high-level waste is the largest concern because it is highly radioactive and can stay that way for millions of years, making it very dangerous to humans and the environment. So if we look at commercial nuclear energy, this map shows the current operating commercial reactors. There are currently 98 active reactors in the United States right now, and the different colors just represent the different regions the reactors are in. But these reactors supply energy to industries and residential homes. And the big question is, what types of reactors are used? So with most reactors, the core heats up water, creating steam, which then powers a turbine and generates electricity, which is what you can see in this picture here. If you want to look at the certain types of reactors, there are two main types. One is pressurized water reactors. They function by using pressurized water in the primary coolant loop, and that carries heat created by the core to the steam generator. Inside the generator, the heat vaporizes and produces steam. The heat vaporizes the water, sorry. The steam is directed to the main turbine, causing it to turn the turbine generator, which produces electricity. The water is then recycled through a filtration system into a condenser where the steam is cooled into water that is then reheated and sent back to the primary coolant loop. The other type of reactor is boiling water reactors, and they function by creating a steam-water mixture made of very pure water and heat which creates the steam. This mixture leaves the top of the core and enters a moisture separation unit where the water droplets are removed and the steam is filtered to the main turbine, causing the turbine to turn, creating electricity. The unused steam is then condensed and reused, like in the pressurized water reactors. In both reactors, the core is cooled by water supplied from different pumps powered by the electric grid. So this means that because they're using energy, they're actually producing less energy than they would if they were not using the electric grid. Now, where does all of this energy created go? These graphs are from the Department of Energy website, and nuclear power is the largest source of clean energy in the US and has the highest capacity factor, making it one of the most reliable energy sources. Capacity factor is the plant's actual generation compared to the matched generation within a given period without any interruptions. Nuclear power plants produced 772 billion kilowatt hours of electricity in 2022, and that is enough power to power 72 million US homes, which is a little over half of the homes in the United States in 2022, according to the US Census data. Nuclear energy is also very dense. So a 1-inch uranium pellet is equivalent to a 149 tons of oil. Gallons of oil. So nuclear energy goes to industries and residents, but in truth, it could power most of the United States. But the main question is, what happens to the waste? So, like we said earlier, there's low and high waste. Low waste is the materials that have been exposed to radiation or radioactive materials, and those are safely stored and disposed of. The major concern is the spent fuel for the reactors, and that's also known as high-level waste. So in the video, you see what happens to the control rods. But after 5 years of use, the rods are removed from the reactors to start the decommissioning process. So first, they are placed into one of these casts that you see being built, and then those are placed into a large swimming pool-sized tank of water, like what you see in the bottom photo. And this is so that the temperature of the material inside stays low and constant. The water is on a filtration system of its own, so that it also stays cool and does not start to overheat. The used fuel rods are placed into these dry casts after being taken out of water, and then they are buried into very similar sized concrete basins within the ground. As of right now, all commercial waste is stored on site or in storage facilities. However, a permanent disposal site has been planned for Yucca Mountain, but we will be talking about that later on. When we talk about transporting the spent fuel, it is a highly regulated process, and every rod is surrounded by 7 tons of protective material for containment, radiation shielding, and impact absorption while on the road. And all waste is tracked and traceable within the United States through the Nuclear Regulatory Commission, the EPA, and the DOE. So looking at the Department of Energy and what they use nuclear energy for, in the past they have used similar reactors. However, recently, the DOE has been focusing on research and technology advancement of nuclear power, which means that they have started to create advanced small modular reactors, which is what this picture is of here. And these are a part of the DOE's goal to develop safe, clean, and affordable nuclear power options. They have a relatively small footprint and have reduced capital investment, and they can be on smaller sites, which means that they can be in more populated areas instead of being out in the middle of nowhere. These reactors also use light water, which means it's light in minerals instead of a mineral-heavy water. And they can also be adapted to use liquid metals, salts, and gases as coolants instead of just water, which has been considered safer and more economically beneficial, and also allows for use in areas where water is not as available. The SMRs are still in the licensing phase, but will hopefully be deployed in the late 2020s. So the DOE uses their nuclear energy for research, like I've already said. One place they do this is at the Savannah River Nuclear Site in Aiken, South Carolina. It's also known as the SRNS site. And something that is site specific to them is the development of tritium. And tritium is a radioactive isotope of hydrogen and is a key element in nuclear science right now. It is only extracted, reloaded, purified, and recycled in Aiken, South Carolina at the SRNS site. It has a very short half-life of 12.3 years, so it must constantly be replenished and remade. And SRS also has the only operating production-scale nuclear chemical separation facility in the US, which means that they can take chemicals apart and put them together for nuclear energy use in other areas. So they'll make those control rods and those fuel rods and then send them to other facilities. The site is also a storage facility for most of the country's excess plutonium. And like I said, the reactors support all of this research and science going on. The site is also in the process of conducting extensive environmental research and monitoring to see the effects of nuclear energy in the soil, water, plants, and animals of the region. So what happens to the waste that they produce? They produce two types of waste out at the site, solid and liquid. The solid waste gets shipped to other facilities for storage due to lack of space. Historically, it has been kept on site in underground farms, like what I talked about earlier in commercial plants. And they follow the same processes, but they're running out of room. So now they ship it to other holding facilities. The liquid waste is stored in tank farms, and they work by forming a sludge at the bottom of a tank. There's a picture of it right beside the liquid waste. It's that large capsule. Sorry. So the sludge is formed in the bottom of that tank. The liquid above the sludge is known as salt waste, and that is concentrated by evaporation that reduces its volume. As the salt waste cools, it crystallizes and forms a solid known as salt cakes. And then those can be transferred and as solid waste. But the tanks have forced cooling systems to keep the material stable, and the design of the liquid waste tanks have changed throughout the years. They're typically made of steel and concrete, and the design is dependent upon the material going into it. However, they are all underground and sealed, and then beside each sealed tank, there are monitoring systems for leaks and containment issues that are monitored on a daily basis. So the environmental impact of nuclear waste, there are three main acts that are important. And it's important to note that remediation work is going on in many locations, and strict monitoring programs have been put into place to ensure that there is limited to no negative impact going forward. Believe it or not, the picture on the bottom with the bulldozers is remediation work going on in D area of the SRS site. So the EPA is responsible under the Atomic Energy Act for developing general environmental standards that apply to both the DOE operated and the Nuclear Regulatory Commission licensed facilities that use radioactive material. So jumping into the Atomic Energy Act of 1946, it establishes the Atomic Energy Commission to ensure that nuclear energy is used for peaceful purposes and that there is common defense and security with a focus on health and safety of the public to ensure that radiation programs are in place for every state, and there's one in place for the federal government as well. The Nuclear Waste Policy Act of 1982 is a little bit different. It supports the use of deep geologic repositories for the safe storage and or disposal of the radioactive waste. The act lays out how and when these geologic repositories are supposed to be chosen. It also provides a timetable for key milestones for the federal agencies that are choosing these sites. And it was the act that approved Yucca Mountain that I will get to here in a minute. The Energy Policy Act of 1992 addresses energy production in the US, including energy efficiency, renewable energy, oil and gas, coal, and it includes nuclear energy and security, as well as climate change technologies. And it focuses on innovating technologies that avoid greenhouse gas production. So it's really the act that's pushing for green energy. I said we were going to talk about Yucca Mountain, and we are right now. So Yucca Mountain is a remotely located mountain in Nevada. And under the Nuclear Waste Policy Act of 1982, Congress assigned the DOE to locate, build, and operate a geologic repository for all nuclear waste. After doing extensive research, the DOE chose Yucca Mountain in Nevada. And Nevada has been against this from the start. They claim that there were major health risks and that the mountain itself is not stable enough to contain nuclear material. Tunnels have been built 1,000 feet below ground, and $100 billion has also been spent. But due to legal issues and it being tied up in the courts, it will most likely never be used. Just because there has been research supporting the state of Nevada's claim that it should not be used due to safety concerns. So the big question is, what are we going to do with all that waste if we can't use Yucca Mountain? And that gets us looking to the future of nuclear energy. So unfortunately, nuclear energy is currently at a Y in the road, so to speak. If we can't find anywhere to put the nuclear waste or anything to do with it, then nuclear energy will most likely die, just because we're going to run out of room to put the byproducts. Also, another issue is the original reactors are older and they need to be repaired or retired. So new innovations and technology need to be developed. Those smaller reactors are a good start in that direction. There's also some countries around the world that are researching how to reuse the spent fuel rods instead of just storing them. And if that research is a viable option, it should be an option for the US as well. So going forward, permanent storage solutions need to be decided upon, and old reactors need to be retired or revamped with new technologies. And new and more efficient reactors also need to be invented and put to use. And then the continued environmental monitoring and research of reactor sites will also be important to ensure that there are no leaks or containment issues moving forward. I really appreciate y'all listening, and I hope you enjoyed. Thank you.